Okay. So last week, we spent a lot of time talking about CP, the constant pressure molar heat capacity as a function of temperature. But in reality, we only want to know how to calculate delta H. So that's for this chapter. You see a lot of problems. They ask you about delta H under different temperatures. So that's the reason why we introduced this formula. And last week I mentioned that there are only maybe 2 or 3 formulas that you have to remember for this chapter. And this is, I think, the most important one. So when you want to calculate the change of enthalpy, you integrate the constant pressure molar heat capacity with respect to temperature. So it says that in the textbook, it says that delta H is the area under a plot of CP versus temperature between T1 and T2. But this claim, this statement is not very useful, actually. So in fact, you only need to memorize this if you don't want to understand these things. But this is basic calculus, right? So if you have a CP to temperature plot, of course, based on the equation you just saw, delta H is the area underneath. And delta H, again, it's QP. P stands for constant pressure, and it's the amount of heat required to increase the temperature of 1 mole of the system, material system that you are discussing about, from temperature 1 to temperature 2 at a constant pressure. Okay? So most of the problems that you're going to go through in this chapter will be limited to constant pressure. For instance, the pressure is limited to 1 atm, and then you change the temperature. Okay? There are some very rare cases at the very end of this chapter that we discuss about the change of pressure. But later we'll see that changing the pressure will only change the delta H by a little bit, especially for solids. If you still remember from last week, we talked about when you change the pressure, there's only a small change in terms of, for instance, internal energy, because the atoms in the solids are bound to each other, so they are hard to move around. So basically, changing the pressure is very hard to change delta H or delta U. So basically, in this chapter, most of the time we'll be focusing on changing the temperature rather than changing the pressure. So that's the reason why we look at delta H, and especially for constant pressure, and then we change the temperature. Okay, so for instance, if we're talking about a reaction for a closed system, and it's undergoing a chemical reaction, or you can say phase transformation. In this case, the example is a reaction. You have A and B, 2 components, and if you put them together, it will go through this reaction and become a compound AB. And if we want to calculate the heat involved during this reaction, the delta H will be the enthalpy of the compound minus the sum of the enthalpy of the reactants. So this is pretty straightforward. I believe that you learned this during the general chemistry during your first year. So delta H is the difference between the enthalpy of the products and the reactants. Well, this is pretty straightforward. And we call this Hess Law. I think probably even in high school you learned this. So if you're having delta H greater than 0, then it means that this is endothermic. Okay, you are absorbing heat. Therefore, delta H is greater than 0. However, if it's less than 0, it means that it's exothermic. So you're releasing heat when you go through this reaction. And the textbook bring up this example. So consider a material. It has 2 different phases. For instance, in this case, this material is named like A. It has 2 different phases. It has solid phase, and it can change. It can be changed to liquid phase. But we are not specifying the melting temperature or the phase transformation temperature. We're just saying that this material can have two different phases. It can have solid phase. It can also have liquid phase. And for solid and liquid phases, they have different dependence of heat absorption efficiency depending on the temperature. Therefore, the CP will be different for these two phases. So if you plot this out, if you plot the enthalpy, H, as a function of temperature, because we know that for solid and liquid phases, they have different CPs. So the slope will be different. So imagine that you have something like this. Okay, so it's different from in the textbook, but imagine that you can have something like this. So this is for solid, and this is for liquid, for instance. And the reason why the slopes are different is because the CPs are different. So this is CP, let's say, A, liquid, and this is the slope of that. This corresponds to the slope of this plot. And the reason why we can say that is because we know partial H, partial T at constant pressure is CP, right? So the slope of this plot corresponds to CP. And we know the reason why we have two lines is because this is liquid phase, this is solid phase. So for example, if you're dealing with some material that will have a phase transformation temperature or melting temperature at Tm, let's say it's here. So the temperature here is called Tm, the melting temperature. Then we know that if you're doing experiment, okay, if you're doing experiment, starting from, say, room temperature is here. Let's say this is 298 Kelvin. You start from here. It will go through this solid line because at low temperature it is solid, right? But when the material is at this point, at the melting temperature, it will become liquid phase. So it will go up and then follow this line. So that's the reason why when you look at H versus temperature plot for several different materials, if you look on the textbook, you'll see this kind of jump. It is because at some certain temperature, the material you're looking at is going through phase transformation. And for melting, we know that this is the melting process. It is endothermic. Which means that delta H is greater than 0, right? But in this example on the textbook, there's no such transformation or melting temperature. It only shows you that, okay, so we have two phases, solid and liquid. And even for liquid, if you go below the melting temperature, you can still be liquid. And that's also true for solid, that you have a line over here. But in reality, when you're doing experiment, you will see typically a plot like this, okay? So that's the difference between reality and the plot on textbook. But this is just an example. This is just an example to show you how to calculate delta H under different temperatures. So imagine that we can have solid and liquid at the same time, under some certain temperature. And they have different slopes in terms of H versus T. And we know that if we're going through a transformation at T1, then the delta H can be labeled as delta H T1. For instance, right now we're interested in delta H under different temperature. Say, for instance, we want to know delta HT2, then what should we do? Or, for instance, this is the normal case. This is a regular melting temperature. If, for instance, somehow we can raise the temperature and then make it transform, make a phase transition at an even higher temperature, then what will happen? Let's say this is Tm prime. So we know that this difference here, is delta H, let's say Tm. But what if we can go through phase transformation at an even higher temperature? Let's say we call this delta H Tm prime. So how can we calculate this? So typically, one of the information will be given. Typically, for instance, delta HT1 is given, and you also know Cp for liquid and solid phase. Then you should be able to calculate delta H2. So the philosophy behind this is very simple. For instance, we know delta HT1 is from A to B. Okay? It's from here to here. Then, based on math, we know that if we do calculations from here, if we add the process from here to Tm prime, or the T2 on that plot, and then this one, and then come back here, we will get the same thing, right? So let's say over here, we start from here, okay, some certain point, and we integrate Cp over this temperature range. So that's the reason why we have a Cp, A solid, integrate over dt from T1 to T2. And then we have this from D to C. This is delta HT2. And then we come back here, follow the liquid line. But since we're moving backward, so we integrate the temperature from T2 to T1. But remember, if you're integrating along the horizontal axis in a reverse way, we can put a minus sign. So if you put a minus sign here, then the direction of integration will be from T1 to T2. Okay? So the concept is that if you add these three up, it should be the same as delta HT1, right? So if it's in this case, then delta HTM, let's say this is delta H1, this is delta H2. Prime. So you have three sections, 1, 2, 3. If you add these three up, then you will get this one. Okay? So based on this concept, we know that, okay, here, delta HT1 is, of course, the phase transformation heat, HAL, the liquid phase, minus the solid phase at temperature 1. And delta HT2 is the difference over here. And this is what I just wrote down. So from A to B, you can consider it as, so let's say, let me use a different. This is A, B, C, and D. So these points. If you start from here, you want to calculate, sorry, it's the other way. If you want to calculate from A to B, it is essentially the same as A to D, D to C, and C to B. So if you know these, how to calculate these, you can calculate this one. And in fact, those are summarized over here. For instance, if you want to calculate this change from A to D, the delta H is fairly simple based on the equation we just saw, because this is following a slope that is defined by Cp. And this is the solid phase. This is the solid phase. So we are using Cpa, but it's a solid phase as our slope. So as long as you know this, you can calculate this difference by using this integration. And that's the same for the liquid part, except that you're going backwards. You're going backwards. So the bottom line is that when you try to calculate this at T1, it is actually the delta H at T2 plus those two integrations. And those two integrations corresponds to, again, this part and this part. So if you summarize that and try to move delta HT to the other side, you can have this, this simple form. So delta H at T2, this one can be represented as this delta H. This is probably the information that's already been given, plus this integration of delta Cp. Because remember that we have integration from T1 to T2, and this is a minus sign here, and we have the A solid minus A liquid, the Cp for solid and Cp for liquid. And we're looking at the difference of those two. So that's the reason why we can summarize that to delta Cp. And delta Cp means the difference of molar heat capacity for the liquid phase and the solid phase. Okay? So please bear in mind that this derivation is very important, and also the result is important. So whenever you want to calculate the change of enthalpy at some arbitrary temperature, then you need to know the information of, for instance, at some certain temperature, the delta H at some certain temperature, and also the difference between these two phases. I mean the heat capacity difference between the two phases you are looking into. So in this case, we're looking at Cp for liquid phase and solid phase. So that's the delta Cp that we want to look into. And typically, if you look at the problems in the textbook, they will tell you these informations. So you won't be, typically, if they don't give you this information, it's impossible for you to calculate. So for instance, they will give you the information of Cp, say A solid, as a function of temperature, such that you can do this integration. Okay, so all the informations of Cp will be given. We'll see some examples later. So if the heat of the reaction is known at one temperature, like I mentioned earlier, then, and also the constant pressure heat capacities of the products and reactants are also known, then the heat of reaction at any other temperatures can be calculated. And in some rare cases, if delta Cp is 0, which means that if the two slopes are the same, then delta HT2 is delta HT1. So this is not hard to imagine, right? So imagine these two slopes are the same, then at any temperatures, the difference between the two will be the same. Right? So this is what this statement's about. But in most cases, during your calculation, delta Cp is not 0, and it's also a function of temperature. Okay. So to summarize, let me see if I have. So to summarize, this is fairly straightforward. Let's say something like this. This is H. This is T. Let's say this is the reactants. So for instance, this line is for the reactants, and this line is for the product. So we're dealing with this kind of reaction. And if we know the trend of enthalpy for A plus B, then we have a line over here. And if we know the enthalpy of the compound AB, it's a line over here. And we can calculate delta H as on certain temperature T1. So this is temperature 1 over here. And let's say the problem asks you to calculate delta H at T2. Then typically, several informations will be given. We'll know Cp of, say, A, Cp of B, and Cp of AB. In order to calculate this, this is actually delta H T1 plus this, right? So the formula is pretty straightforward. And this delta Cp here is the Cp of reactant, the product minus the Cp of the reactants. So this is for the product. And these are for the reactants. So this is an example. So the textbook shows you the example of like phase transformation. So you have, for instance, a liquid phase over here and a solid phase over here. But in most of the problems, for most of the problems in the textbook, they're asking you about the chemical reactions. So this is a more common case, that you have the Cp for product minus the Cp for reactants. And that's the delta Cp that you want to plug in. Okay? And typically, for most chemical reactions, this is not zero. Okay, because the heat capacity for product will be different from the sum of the heat capacity of a reactants. So typically, this is not zero. Okay, so this statement is not that useful, actually. But please bear in mind that this is the formula that you will see throughout this chapter and for problem sets. And another important thing is that H does not have the enthalpy does not have an absolute value, and that is only changes in H can be measured. So typically we're talking about delta H instead of H itself, because enthalpy, we know that it's not an absolute value. So but there's a convention. So on the textbook it says that it is convenient to introduce a convention which will allow the comparison of different enthalpy temperature diagram. So if you're dealing with a lot of different reactants or a lot of different chemicals, we want to set up a standard such that we can compare them with each other. And in this case, the convention states that the enthalpy of elements in their stable states, equilibrium states, at 298 Kelvin at room temperature is assigned to be 0. So this is the convention from chemistry, from chemist people. And I believe that in the general chemistry class, probably you've already learned this. For instance, for pure elements, for instance, if you're talking about oxygen, at room temperature, then H is assigned to be 0. So if you're dealing with just elements like aluminum, like oxygen, and gold, at room temperature, then we'll assign a value of H to them, and that value will be 0. But the enthalpy of a compound is the heat of formation of the compound, from its elements at 298 K. So for instance, if you are talking about like H2O, like water, then we know that the H or the enthalpy value assigned to H2O is not 0 for water, for H2O. But if you're talking about a hydrogen or oxygen alone, then the values for enthalpy for those single elements will be 0. So this is an example. If you're dealing with a simple oxidation process, the reaction is from a metallic, for instance, solid, let's say iron or something like that, or aluminum, and then you have the metal to be interacting with oxygen, and then it will form an oxide called MO, some metallic oxide. And we're talking about a reaction happening at room temperature, so it's 298 K. And the delta H for that will be, of course, the enthalpy of the products minus the enthalpy of the reactants. And we know that by convention, the enthalpy for these two will be 0. So all you left is the enthalpy of this metallic oxide. Or you can say you artificially change the enthalpy value of those two such that delta H is assigned as the enthalpy of this metallic oxide at 298 K. Okay? So if you look at a textbook, you'll see a table. If you go back to, for instance, like page 653, you'll see a lot of different delta H for different kinds of oxides. But typically, you won't see the delta H or the enthalpy values for single elements because those are already assigned to be 0. Okay? So, but for compounds, typically you have this value. Allows you to look up, in the appendix. And for example, if you're talking about, say, lead oxide, the variation heats of chemical reaction with different temperature, but at constant pressure, we can look at an example of oxidation of lead, Pb is lead, to form lead oxide. And the example is pretty straightforward. The formula is the same as what we just saw earlier over here. So you have a single atom, for instance, a mole of lead, and it's interacting with like 0.5 moles of oxygen gas, and it will form lead oxide. So if you plot this reaction out, plot the enthalpy of the two reactants and the product out, you'll see a plot like this. Typically, you'll see that enthalpy is always going upwards, like all the plots that we see over here, because we know that when you dump dump heat into the material, the H will go up. So when you raise the temperature, the H is always going upwards. So Cp is always a positive number, at least in most cases. And if you look at those two reactants, we have lead, we have oxygen. So oxygen is always in gas form, at least above room temperature. It's always in the gaseous form. So you don't have to worry about phase transformation. But lead, on the other hand, will go through a phase transformation from solid phase to liquid phase at, say, around 600 Kelvin. Okay? So you'll see a jump. Like I mentioned earlier, if you go through a phase transformation, typically you will see a jump in the enthalpy to temperature plot. So that's the case over here. But if you look at lead oxide, the PbO over here, that's the product, there's no such phase transformation. Okay? So lead oxide is very stable. So even when it is heated up to 700 Kelvin, it is still solid. Okay, it is still solid. So it's a pretty straight line, and there's no jump, which means that there's no phase transformation. There's no melting of lead oxide up to, say, 1,000 Kelvin. And if you look at the intercept, for lead oxide, the intercept to 298 Kelvin, or around 300 Kelvin, is this value. It's about minus, say, 220 kilojoules. So that's the formation heat of lead oxide. And if you look at lead and oxygen, if you look at these two, they will start from 0. Okay, they will start from 0. And the reason why they start from 0 is because that's by convention, that pure elements, for pure elements, the enthalpy at room temperature are assigned to be zeros. Okay, so they will start from 0, and when you go up to higher temperatures, because the Cp is positive, so you have positive slope, so they will go up. And for lead, over here at point B, which is about 600 Kelvin, it will go through, say, a phase transformation from solid phase to liquid phase. So we'll go up and then keep going up. And for oxygen, it's just a straight line. There's no phase transformation. So this is an important plot. Please make sure that you understand why the plot is like this. And this difference over here is the delta H of this reaction. Remember, like when we talk about the enthalpy for a metallic oxide, it is actually the delta H, the heat of formation at that temperature, at 298 Kelvin. So the reason why we start plotting lead oxide from this point is because we know that for this reaction, it is an exothermic process. So it will release heat, and therefore delta H is negative. So we'll start from here. And then lead oxide has its own Cp, so it will have this slope going upwards. Okay, so the next slide is more complicated because if we want to do calculation, typically this is what I do. I typically will plot the, so the question, I mean the problem typically will show you some information. For instance, we're talking about some certain reactions. So I'll try to sketch, the enthalpy as a function of temperature for all those reactants or products involved in this reaction, and then figure out the slope and the transition temperature. Okay, to make sure that you can assign, the information to each section. And like I mentioned earlier, for lead oxide, the enthalpy for that is the formation heat. Therefore, this minus, let's say, 220 kilojoule per Kelvin. This is for the, sorry, I think this is joule. This is not joule per Kelvin. So I think the textbook was wrong, at least for the last version. So please change this to joule, not joule per Kelvin. And for each section, you'll see the slope, right? For instance, for lead oxide, it will start from this value, and it will gradually go up. And to calculate that change, you have to do the integration over the Cp of lead oxide. And that's the same for each reactants. For instance, for oxygen, you integrate that over the Cp of oxygen. And for lead, it's the same. However, later we'll see that if your system or your material is going through phase transformation, then you have to add this delta H melting, which is the melting enthalpy, into your formula. So you can see that over here, you have delta Hm of lead. And that takes place at like 600 Kelvin. Okay. We'll come back to this And if you have questions regarding the exam, please go to the TA. Okay. So let us come back to this problem, lead oxide. In order to figure out what's going on in this plot, so I plot it again over here. And typically, if you look on textbook, this is my way of doing it. Typically, I'll write down, like if the problems tells you these information, I'll try to understand like what are the information that I need to interpret this plot. So the first thing that a textbook tells you is that for lead oxide at room temperature, the formation heat is minus 21, minus 219 joule. I think it should be joule instead of joule per Kelvin. So if you are reading the textbook, please make sure that you change that to joule instead of joule per Kelvin, because joule per Kelvin is the unit for entropy. Okay? So that should be joule, the first one. And if you look at this plot, you know that it's from this point 298 Kelvin, and it should go down to minus 219,000 joule over here. So that's for lead oxide. And for the reactants, we have that the heat capacity given as 23.6 plus this 9.75 times 10 to the minus 3 T. Therefore, this is a function of temperature. So if we look at lead, we know that there are two sections. One of them is for the solid phase, here. And liquid phase is here. And this is the phase transformation or the melting point of lead. So if you're below that melting temperature, you have to use the heat capacity of solid lead, which is given by this formula here. So it's a function of temperature, and typically when you do the homework or when you try to solve the problems in the textbook, either the textbook will tell you, or you have to look up in the appendix. That's again like page 650 something. You'll see the 652. You'll see the table A2 has a lot of different values for the CP, and typically that's a function of temperature. And sometimes you'll see like two terms for each one, but sometimes you'll see three of them. For instance, like oxygen, you have this constant term, you have this first order coefficient, you also have a third term that is proportional to T to the minus 2. Okay, so it really depends on like how many terms you want to approximate the heat capacity as a function of the temperature. Okay, so for this one, in order to calculate, for instance, the slope from here to here, we have CP. And for instance, if we want to start from here to this point, we know that delta H is, for instance, 0 plus CP of lead, and it's a solid phase. This is a function of temperature. And we start from 298 Kelvin to the melting point of lead. Okay, the melting point of lead. If we want to calculate here from here to here, so this is what you will need. And typically, the melting enthalpy will also be given. So in this case, it is around 4,800 joule at this melting point. which is 600 Kelvin here. And for oxygen, you only need one CP value. That's already given, from 298 Kelvin to 3,000 Kelvin. And typically, we don't go up to that high, so we don't have to worry about that. And the melting temperature of lead oxide is 1159 Kelvin. So that's also much greater than the plot over here. So if you go up to, for instance, here, go up to, say, here, you probably, this is the melting temperature of PBO. You probably will see a jump over here at, this is 1159 Kelvin. But on the plot, on the textbook, it is below that melting temperature, so you don't see that jump. Okay? You only see one slope over here. So if we want to calculate delta H of this reaction under different temperatures, typically we will add the two reactants together. So if you add these two lines together, which is lead and oxygen together, you'll see the combined line over there on textbook. So this is a graphical representation of what this reaction is doing. Okay? So if you want to calculate delta H for this reaction, for instance, if it's at 298 Kelvin, then we already know that the delta H is this value, right? So that value is this. But what if we want to calculate, say, on that plot, maybe 500 Kelvin? What would that be? So if you're dealing with 500 Kelvin, it turns out that it will be the difference from F to G, right? And we're lucky that we're not going through the melting temperature, so we don't have to worry about the melting at this point. So we don't have to worry about this jump over here. So if you're just trying to calculate Fg, so this is, let's say, Hf minus Hg. Then again, we can use the same trick, right? We can do the same trick as what we did earlier, that we know F to G will be the same, or G to F will be the same as G to D, D to A, and A to F. Or if you just remember the formula, then it is more straightforward. This will simply be delta H 298 Kelvin. This is already known, right? This one. Plus 298 to 500 and delta Cp dt. Then it's done. I mean, at least writing the equation. I mean, it's done. But you have to do the hard work to plug in all the Cp's into this formula and then to calculate that. So in this case, the delta Cp is what? You have Cp of lead oxide, that's the product, it's in the solid phase, minus Cp of lead. And for 500 Kelvin, it is in the solid phase. And also, you have the Cp of oxygen. It's in the gaseous form. And remember, for oxygen, it is only 1/2. So you need to put a 1/2 over here. So let me rewrite that over here. I'll erase this one. This is what we want to calculate. So at 500 Kelvin, what will be the delta H? And the key information is to figure out delta Cp. And in this case, it is lead oxide minus, say, Cp of lead in the solid phase plus 1/2 the Cp of oxygen in the gaseous form. Something like this. Right? And those information already be given. So all you need to do is plug in the relevant information and then do the calculation. Okay. So that's the case when you are discussing the temperature that is below the melting temperature of lead. Okay. So I won't go through this again. As you can see, we want to figure out what delta HT is, for instance, at 500 Kelvin. And then we will use this formula to calculate. The most important thing is you have to figure out what is delta Cp. And in this case, the delta Cp is the Cp of product minus that for the reactants, as I mentioned in the last class. But please bear in mind that you have to follow this reaction equation that you have only 1/2 mole of oxygen here, so you have to use 1/2 over here. So I think that's it. That's the most important thing in this chapter, like how to calculate this or this. So in this case, I won't write it down again. For delta Cp, if you plug in the information given by the textbook, you'll see something like this. And then you can do the integration, and you can figure out, like at each temperature, what will be the delta H. So if you're dealing with 500 Kelvin, it's lucky that the delta H is still having the same trend, so you don't have to worry about the melting of the lead. However, if you go beyond 600 Kelvin, then you have to take the melting of lead into account. So that's the reason why for delta H, there's a jump at 600 Kelvin as well. So that's the same as, that's due to the melting of lead. But of course, if you're just talking about lead oxide alone, there's no such jump. But if you are talking about the delta H, which is the the reaction enthalpy, then of course there's a jump over here because that's due to the melting of the lead. Which means that if you are trying to calculate, for instance, if you want to know delta H at 700 Kelvin, then you cannot just use this formula, right? Because we know that the Cp will change for this one. So this delta Cp is only valid for temperature up to, say, 600 Kelvin. So this is important. So this delta Cp is only valid for temperature range in between 298 Kelvin to 600 Kelvin, because we know that 600 Kelvin is the melting temperature of lead. So beyond that point, this value will be changed. right? This temperature dependence will be different. So that's the reason why table 1 also tells you the CP of lead in the liquid form, and as well as the delta H melting for this phase transformation, because you have to take that jump into account over here. And beyond that point, the slope will also be different. Okay, the slope will also be different. So in order to calculate the trend along this line, you actually have to add the delta HM. And also, you have to separate the CP contribution into 2, because you have that for the solid phase, and then you also have a different contribution for the liquid phase. So imagine that you start from here. You gradually increase up to like 600 Kelvin. And then at 600 Kelvin, this will have a increase due to delta HM, that's the melting, and then you'll keep moving upward. And that's this part. That's this part. Okay? So if we want to do the calculation, we have to take that melting and also the liquid contribution into account. So that's the reason why for the liquid enthalpy of lead, you have to integrate that from 298 to 600 Kelvin, and then take this delta HM into account, and then start from 600 to the temperature that you want to discuss. For instance, here we want to talk about 700. So it turns out that if you do the calculation, this is what you will get. The delta HT at a temperature that is greater than the melting temperature of lead, you will start from, again, this original value, delta H298, and then you add this term, the original delta CP, this one, up to 600 Kelvin, and then you minus the contribution of delta HM from the lead due to the melting, and then add another one over here. So the bottom line is that you're still using the same formula. Except that here you have to take the melting into account. So a general expression is that if this temperature is greater than the melting temperature of lead, then you start from the 298 Kelvin value, which is already given, and to Tm, which is 600 Kelvin in this case, of lead. So this is delta Cp, let's say delta Cp1, and then minus delta Hm of lead. And we'll start from 600 to the temperature you want. And in that case, you have a different Cp, right? For lead oxide and oxygen, those two are the same. But for lead, because it changes from solid phase to liquid phase, so this is different. Okay, this is different. So in this case, lead oxide solid minus, let's say, Cp of lead in the solid phase, and of gas. Right? So in this case, Cp1 is still using the solid phase of lead as their Cp calculation, but here for delta Cp2, it is the Cp of lead oxide in the solid phase minus Cp of lead, the liquid phase, oxygen, the gaseous form. Okay, so it should be pretty straightforward, right? So it turns out that the textbooks use the 1,000 Kelvin to plug in, and turns out to be a certain value. But please bear in mind that whenever you have a jump in the H versus temperature plot, you have to look for the change in terms of Cp. Okay, so here, it's over here. And here you have a minus sign. This. So based on my experience, typically, if you're dealing with this kind of reaction, if you have a melting process in the reactants, so if you have any melting here, if you just want to memorize this equation, just use a minus sign here. But if you have a melting on the right-hand side, for instance, it's the product that is having the melting, then you use a plus sign over here. That's pretty straightforward, right? Because if you have the melting on the right-hand side, then it's a positive sign. But if you have a melting over here, you have to subtract that from the calculation. So we have a minus sign here. Okay. So this is a very important example of how to calculate delta HT at different temperatures, especially when one of the reactants is having phase transformation. So if you have phase transformation, you have to divide your calculation into like several different sections. Okay. But if you're dealing with like just, for instance, 500 Kelvin, if you want to know like T to the 500 Kelvin, then you don't have to worry about the second part, right? You don't have to worry about this part, and you don't have to worry about this. Because if it's, the reaction is carried out at 500 Kelvin, then there's no melting of lead. Okay? So care must be taken with the signs of the changes in enthalpy during phase transformation. For instance, if it's in the reactants, you have a phase transformation of lead. In this case, you have to subtract that out of your calculation. And more importantly, for different phases, here the lead has been turned into liquid, you will need to use a different Cp or delta Cp. But lucky enough, the phase transformation that we're talking about typically, for instance, from low to high temperature phase, is always endothermic. So this delta H is always, the value itself is always positive, right? Because it's either melting or vaporization. So they are always positive. The only thing that you have to worry about is putting a minus sign in front of it or positive sign. So it's a minus or positive. That depends on, it is the reactants or the products. Okay. If it's the reactants, then it's the minus sign. If it's the product, then you will have the plus sign. And the reason why this is greater than 0 is because there's a latent heat of melting. You have to supply enough heat in order to melt something or to vaporize something. And so the bottom line is that if you want to calculate something, you have to use this one. But if you're going through some phase transformation for the reactants or the products, you have to put in the delta HM for that. Okay? So this is just another derivation for getting that equation. Actually, we've already derived this before. That I don't want to go through this again, but because partial H, partial T is Cp, therefore, if you go through that, in the end, you'll get the same equation. So the bottom line is that this equation is very important, and typically for the calculations in the textbook, they will give you enough information which allows you to do that numerically. So we've already discussed the calculations of enthalpy. Now we want to talk about the calculation of entropy. And it is, again, very straightforward. And I've already mentioned this last week. So for delta S, of course, based on second law, it is delta Q over T. And if we're doing the process, again, at a constant pressure, which is a isobaric process, then this delta Q is simply dH, right? It's only enthalpy. So it turns out this is Cp dt. And therefore, ds is simply Cp dt over T. So I mentioned last time that to calculate delta S, you use almost the same equation. So for delta H, we have delta Cp dt, and we do the integration. But for delta S, we use this formula. Okay, we use this formula. So from a certain temperature T1 to T2, for instance. Okay. So the change of entropy, based on this, it is the area underneath the Cp over T versus T plot. But this is not very useful generally. So again, if you want to remember, just remember this. It's not necessary to use the Cp over T versus T plot. This is not very useful. So basically, typically you have to go through the calculation, and you are not using this area method. So that's the reason why I have a remark here. This is not useful generally. So if you want to calculate the entropy of a certain of a material at some certain temperature, then based on the equation that we have, we know that if this is 0, this is just a certain temperature, then we know that S at a certain temperature can be represented as the S from the 0 temperature plus this, right? So if we can integrate this from 0 to some certain temperature, and more importantly, if we know what is the value of entropy at 0 temperature, then we can calculate the entropy of this material at any temperatures. So this S0 stands for the molar entropy of the system at 0 Kelvin. Okay. So an important thing is that we need to know what is this value down to 0 Kelvin. And that is related to the so-called the third law of thermodynamics. So I'll talk about the conclusion first. So most of the time we'll assume that S0 is in fact just 0 at 0 temperature. So let's say the third law postulates that this is very, very close to 0 at 0 Kelvin. Which means that for all the materials, if third law is true, that for all materials down to absolute 0 temperature, the entropy is 0. Okay, there's no randomness. So the third law is trying to define an absolute value of entropy for materials at 0 temperature. And it postulates that it should be 0. Okay, it should be 0. So Nernst, a chemist back in the early 20th century, postulates that for a chemical reaction between pure solids or pure liquids, the Gibbs free energy as a function of temperature, if you look at the slope, and also the formation heat or the enthalpy change as a function of temperature, the slope of these two should approach 0 as the temperature approaches 0 Kelvin. And those are found by experiments. So through experiments, they actually found that this trend, this one and this one, they're all approaching zeros when you cool down to 0, very, very low temperatures. So that will give us a graphical representation. This is, I think, slightly different from what you see in the textbook, but essentially they're the same. Just the sign is different. This is from the last version. Let me plot it this way. So we have the temperature, and we have the, let's say, the Gibbs free energy. It is going upwards. This. So here, at this point, delta G at this temperature is 0. So this value is delta G. The difference in terms of Gibbs free energy. Okay? And if we cool down to 0 temperature, this is by experiments. They found that the slope of this delta G as a function of the temperature is gradually approaching 0. So the slope here, let's say partial delta G, partial T, this is close to 0. This is close to 0 from the experiment. And the second thing is that partial H, partial T, so partial delta H, partial T is also approaching 0. But first of all, we need to figure out what is delta H T on this plot, right? So let us say we look at some certain temperature here. Sorry. This point. And for this point, we know that there's a tangential slope which corresponds to slope being minus delta ST. So this slope is as this temperature, the delta S will be the slope of this one. And we know that let's see, let's remove this one. For this reaction, if we write down the definition, the Gibbs free energy change at this temperature will be the enthalpy change at this temperature minus T delta ST. So we know that, in fact, the argument that we just brought up, that the slope is minus delta ST, is due to the fact that here. Okay? So more importantly, minus delta ST corresponds to this. This is delta H. How to say that? T delta ST. And therefore, this is delta H. Right? If you look at the plot over here, so this is delta H, this intercept over here. Delta HT plus this is delta ST times T. But this is a minus sign. So basically, you'll retrieve the delta G over here. So here is delta G. temperature. And here you have the minus T delta ST. I think this is much easier to understand using this plot. And this is the slope. Okay. So which means that this point is delta HT. This point over here. So if you change the temperature, for instance, if you go up to higher temperature, you'll expect that the delta HT is becoming greater and greater, which is more and more negative, right? So in fact, delta HT should follow this curve. This is delta HT. So you have a delta HT going downward like this. And they all converge to this point. Because at that point, when T is 0, delta HT should be the same as delta GT. And if you look at the trend over here, you'll see that the argument is true that the slope over here is also close to 0. So partial delta H, partial delta H, partial T is also approaching 0. Okay? So the two important lines over here is, first one, this is delta G as a function of temperature. So we'll go down like this. And the second one is this one. Okay. I think in your textbook, I think it's somehow reversed. Delta G and delta H is reversed, but the concept is the same. The concept is the same. The reason why you have one curve here is because based on the definition of Gibbs free energy. Okay? So at this point, you should expect that the slopes for delta G and delta H are both zeros. Okay, are both zeros. So this is a graphical representation of what this Nernst postulation is about. Okay. So as temperature is going to 0, the slope of the lines, for these two are both approaching zeros. Okay, and therefore, when T is approaching 0, we should know that delta S is approaching 0, right? Because we know that this is approaching 0. Let's write this down again. So we don't need this anymore. We need this one. So once you already know that, you don't need these things to tell you. We only need the definition. And we know that this thing, constant pressure, this is minus delta ST. This is approaching 0 as T is approaching 0. Right? This is the first thing. So delta S for a certain temperature is approaching 0 when the temperature is close to 0. So at this point, delta S should be 0. And the second thing is that delta Cp should be 0, should be close to 0. And the reason for that is through the derivation over here. Okay? If you start from this equation, and then you take the derivative against temperature, and you'll see that here you have the first term, and because you have two variables here, so we have to take the derivative of the, for instance, the first one here, and it will become minus delta S. And for delta S t, it is this term over here. So we already know that partial g, partial t is minus S, or partial delta g, partial t is minus delta S. Therefore, we know that partial delta h, partial t is the same as t, partial delta S, partial t. And this is delta Cp. Right? This is the difference of heat capacity, or molar heat capacity. So if these are all going to 0, that's based on the experiments. So these two trends were found experimentally. Therefore, we know that delta S and delta Cp should both approach 0 as t approaches 0. Okay. So the argument here is that first of all, if you don't really understand, this is minus delta S. It is going to 0 as t approaches 0. That's from the slope of here. But there's another one, delta ht. The slope is also approaching 0 when you go down to 0 temperature. So this one is in fact delta Cp, right, at some certain temperature. This is also going to 0 as. Okay. So if you don't know the arguments, if you want to go through the arguments in the textbook later, I think this is a good summary. Like if you have these two plots, and you know that the slope of this one is actually related to the entropy, it is going to 0 when you go down to 0 temperature. And the enthalpy corresponds to the slope of this entropy to the temperature plot is related to the difference of molar heat capacity. This will also go to 0 when you go down to 0 temperature. So if Nernst postulation is correct, then it means that when you go down to 0 temperature, both the delta S and delta Cp should go to 0. So another theorem was proposed by Nernst, that for all reactions involving substances in condensed states, in solid states, delta S should be 0 at the absolute 0 of temperature, right? So delta S for a certain reaction, we know that is, for instance, A plus B will become AB, will be something like this. And this will be 0 at t equals to 0. So if you further assign, like we mentioned earlier, that for pure elements, Sn and Sb are in fact zeros, then you know that the compound, the entropy of the compound will also be 0. So in fact, if you don't know all these derivations, if you just want to memorize what the third law or this Nernst postulation is about, you can just simply put that when you go down to 0 temperature, the entropy of all materials for pure elements and for compounds should go to 0. Because that's the case when you have delta S is approaching 0 and delta Cp is approaching 0. Okay. So these are just the mathematical arguments based on the experimental results. But this is more like a theorem. So based on these experimental results, Nernst postulates that this is the case. Okay, this is the case. So the third law of thermodynamics, although this is hardly a law, later we'll see a lot of exceptions. But the third law, that's what we call it right now, states that when the temperature go down to 0 Kelvin, the entropy should also go down to 0. Okay? So when you go down to 0 Kelvin, all the entropy, all the randomness should be gone, and the entropy for all compounds or pure elements will be 0. But this is incomplete. The incompleteness of Nernst's theorem has been pointed out by Planck. So Planck suggested that only the homogeneous substance can have this kind of condition. Because imagine that your materials have some dislocation or defects or vacancies in it. Even when you cool down to 0 temperature, those defects will still be trapped in your material, right? And as long as you have some defects, there will always be some randomness. Therefore, the entropy is impossible to be 0 at 0 Kelvin. So Planck suggests that only for homogeneous substance, and when it is in complete internal equilibrium, then the entropy may be taken to be 0 at 0 Kelvin. So this is so that's the reason why for third law, a lot of people suggest that this is not a law. It's more like I say a postulation that it's really hard to go down to 0 Kelvin, and it's really hard to verify that this is the case. And for most substances that we're dealing with, they are not perfect. So for non-perfect materials, it is impossible to have a complete internal equilibrium because you always have some defects or dopants or vacancies in your materials. There are a lot of examples in this textbook. For instance, glass. Glass is a metastable state while comparing to crystalline materials. And typically, it is not in equilibrium. So we know that for glass, you can think of it as a very slowly moving liquid, right? I think during the, material science, introductory material science course, if you learn about glass, you know that it's actually more like a liquid, but the movement of those molecules are very, very slowly. So even when you cool down to 0 temperature, as long as it's in the glassy form, it's not in the perfect equilibrium with the environment. So a glass cannot have an internal equilibrium even down to 0 Kelvin. So it should have some certain amount of entropy or randomness at 0 Kelvin. Okay, so that's one example. And of course, then if you have a mixture of atoms, like if you're dealing with alloys, and you have dopants in your material, and you always have some certain degree of randomness, even when you cool down to 0 temperature, right? So that's also a non-equilibrium degree of order. So I won't read this through, but you can go through that in textbook. And the last two examples are more straightforward. For instance, isotopes. Typically, if you look at a bunch of elements, there's a certain ratio of isotopes in it, right? Depending on the species of elements that you're talking about. But typically, you'll have isotopes. So as long as you have isotopes, it means that they have differences among them. Therefore, even when you cool down to 0 temperature, you can have a finite number of multiplicity. Therefore, the entropy of mixing can occur even at 0 temperature. So the entropy does not really decrease to 0 at 0 Kelvin. And only a pure crystalline solid can do that. But if you have some vacant lattice sites, I think you already know what vacant means. For instance, you have a macroscopic vacant sites like dislocation, then you know that even when you cool down to 0 temperature, there's still many different possible locations for the dislocation or those vacancy to occupy. So you have different possibilities. Therefore, as long as you are dealing with non-perfect crystals, the third law will also not going to happen, because when you go down to 0 temperature, the dislocations, the vacancies are still being trapped in your materials. And of course, from material science, you already know that there are different crystal orientation. That's what we call the polycrystalline structure, right? If you're dealing with single crystal structure, then there's no different crystal orientations in the bulk of material. But if you're dealing with polycrystalline material, you have different orientations of the lattice structure. Therefore, even when you cool down to 0 temperature, there's different possibilities that will occur for the orientation of those crystal lattices. So in that case, the third law will also not help. So these are the exceptions that might happen to prevent this from happening. Okay? So please bear in mind that this third law is only more like a postulation. But in reality, typically you will see some finite entropy at 0 temperature. Although those numbers will be small, but there's still some finite values. Okay, so I'll stop over here and we'll finish chapter 6 later. So this is probably the last part of chapter 6. So we just mentioned about the third law, that the entropy in the ideal case, if you have a perfect material, then it should be 0 at 0 temperature. Okay? So there are several ways to verify that. So here's an example, like how to do that experimentally. So just consider a phase transformation for an element from alpha to beta phase. So this material might have allotropes. So it means that, for instance, like tungsten, you have alpha phase and beta phase, and you can have this kind of phase transformation, although both of them are still in the solid phase. Okay, so there's no melting involved. So if that's the case, we can plot out a schematic or graphical representation like this. Imagine that alpha and beta phase can both exist at 0 Kelvin. And if you go up to some phase transformation temperature, and it can convert from alpha phase to beta phase. So actually a better way to plot this, this is the way that the textbook plot this, but in reality, perhaps this is much better. Like if you consider temperature like this, and let's say this is 0 Kelvin, this is off. Let's say this is alpha, so this is, let's say, transformation. So imagine that this is the transformation temperature from alpha to beta phase. So this is beta phase, this is alpha phase. Okay? And for this transformation to happen, there's a certain amount of heat involved, which is delta H transformation. So this is from alpha to beta phase. And if we want to calculate the change of entropy, for instance, at 0 Kelvin, in fact, we hope that from beta to alpha phase or from alpha to beta phase, the delta S should be 0. So what we want to see is this one, right? Is delta S alpha to beta at 0 Kelvin, is it going to be 0? And the way that we calculate this is actually go up to the melting temperature, or sorry, not the melting, the phase transformation temperature, and calculate this. So we know that the delta S here, let's say this is delta S4, should be delta S1 should be this, delta S1, delta S2, and delta S3. Okay? And if we can verify that if you add these three up, it's the same as delta S4, or it is close to 0, then we can say that we experimentally verify that the third law is valid. Okay, the third law is valid. And to do that calculation, we use these three information. So first of all, we know that for alpha phase, there's a certain CP, and the calculation is done by using the formula that we just saw. Right? To calculate delta S, we use the integration of Cp over T. And we start from 0 temperature to the transformation temperature. That is from here to here. And then we add this transformation entropy change. And this is much easier to calculate because we already know for the phase transformation to happen, there's a latent heat of this amount, and the temperature is at, say, the transformation temperature. So delta S2 is just delta H transformation over this temperature. For instance, later we'll see that when we're dealing with melting, this is delta Hm over the melting temperature, right? So it really depends on what kind of reaction that you're talking about. Here we're talking about phase transformation, so I use trans over here. But if you're dealing with melting, then you use delta Hm. Okay. And for this section, like coming backwards over here, again, we use the beta phase because now it is in the beta phase. So here is the alpha to beta transformation. And now we're in the beta phase and we want to cool it down to 0 Kelvin. So the integration is from the transformation temperature to 0 Kelvin. And then we do that for Cp in the beta phase. Okay? So here is the alpha phase, here's the beta phase. So this graph is essentially this turning by 90 degrees. Okay? It's turning by 90 degrees. And we want to calculate this to show that if the third law is valid, then this delta S4 should be close to 0. And if we calculate that, so this is the formula for calculation. We don't have to go through that. So these are the numbers that we will put in for instance, sulfur. Okay? And there's a orthorhombic to monoclinic of transformation, and that will take place at 370 Kelvin, or 368.5 Kelvin. And if you put in the Cp values, or the Cp as a function of temperature that is given by the problem into this equation, you'll see that you can calculate delta S1 and delta S3 for the two different phases. And you can also calculate delta S2 based on the delta H transformation and the transition temperature that the problem gives you. So it turns out that if you add these together, this value is close to 0. Or if you add these two up, like 36.8, not A6 and minus 37.8, it's roughly like minus it's minus 0.94, which is close to 1.09. So if you add these three together, then it's a value that is close to 0. So the point here is to show that this is what we don't know. And this is what they call the third law delta S. We want this to be 0. But this is the sum of all these three. And these two can be calculated by the CP of alpha and beta phase respectively. And this can be calculated by this expression. And we realize that this is, say, 0.94. Let's say this is how much? This, right? Or, I don't know. My math is, yeah, I think this is. This is close to 0. So you have like 0.15 joule per Kelvin if you add all these three together. If the third law is true, we know that at 0 Kelvin, this should be 0. But from the experiments, this is 0.15. This is what we got. And that is already close enough. And the reason why we have a finite value, which is not perfect, is because due to the condition that we mentioned earlier, in this case, it's probably due to the crystallographic orientation, right? Because if you're dealing with a polycrystalline material, then you still have some finite value of entropy at 0 Kelvin. So if it's not perfect, then you always have a certain amount of value over there. So, but the argument here is that if this difference between experimental and third law entropy changes is less than the experimental error, then the equality is taken as being experimental verification of the third law. So in other words, if this number is small enough and it is close to the or less than the experimental error, then it means that we verify that the third law is valid for this case. Okay, for this case. So let us assign that. That's the reason why at the very beginning I said typically we just assign the entropy at 0 Kelvin being zeros. Although it might be, say, 0.1 or 0.0 something, but you can roughly say that it's close to 0. So let us assign that to be 0. Then for a certain temperature that is below the melting point, you can calculate the entropy like this. So from 0 to some certain temperature, and then you integrate Cp over T over a certain range of temperature. And for 298, at room temperature, then this value is no longer, so please bear in mind that this is different from enthalpy. For enthalpy, if you're dealing with a pure element, we assign that value to be 0 at room temperature. But for entropy, for 298 Kelvin, we have to integrate that from 0 to 298. Okay, so this is the difference between enthalpy and entropy. Okay. However, if you're dealing with a temperature that is greater than the melting point, then you have to take the melting process into account. So similar to what we did for the calculation for enthalpy, if you're going through some certain phase transformation point, you have to separate your integration into different sections. You start from S298, and then from 298 to the melting point, and then you add this change, delta Sm, and then from the melting point to the temperature that you want. So this delta Sm, again, is defined as the melting enthalpy or the latent heat of the transformation over that melting point temperature. So there are some postulations, again, on what this value should be. And Richer's rule, based on some observation from the experimental values, states that the entropies of fusion or melting of metals should have the same value. So this is actually a very rough estimation, because if you look at the experimental data, you'll see that it's pretty scattered. Although the linear trend seems to be valid, but you can also see that the deviations from this straight line is by a huge amount. So for FCC metals, at least from the fitting, it should be around 9.61 joule per Kelvin per mole. This. I cannot modify it here, but so this should be joule per Kelvin per mole. Okay. So I forgot a Kelvin here, because this is the slope of this plot. So for different metals, for FCC and BCC metals, although the slopes are slightly different, but you can see that for melting to happen, the change of entropy is typically around the order of, say, 9 to 10. 9 to 10. So this is for melting. This is for melting. And if we look at boiling, that's Troughton's rule. The molar entropy for boiling or vaporization of a liquid metal from liquid to vapor is around 90, or it's 88. But in reality, it's also very scattered. Although you can see that the latent heat as a function of temperature seems to be a linear trend, but for FCC and for BCC materials, they have different values. But you can see that the slope is much greater than the melting ones. So for boiling, the delta S boiling is typically, I would say, around, say, 100 joule per Kelvin mole. So this is for boiling. And this value is, of course, much bigger than, the other way. Much bigger than the melting ones. And this is consistent with our intuition, right? Because for boiling, you're transforming from liquid to gas. And we know that the randomness for gas is the maximum, right? And that for solid, so this is from solid to liquid, and this is from liquid to gas. So of course, the change of entropy from liquid to gas is greater than that for from solid to liquid. Okay, so these are just some rule of thumb that shows you from experiments physicists or chemists, they try to estimate that the change of entropy for phase transformation from solid to liquid is much less than that for the boiling process or vaporization process. Okay, so this is pretty straightforward. Again. Therefore, if you look at a chemical reaction, which involves the reaction of the solid element and the gas. For instance, again, let us look at this classic example of lead and oxygen becoming lead oxide. The change of entropy for that is again, the entropy of products minus those for the reactants. But in this case, since for the reactants, they are in the solid phase, but the product here is in the solid phase. And also this reactant, lead, is in the solid phase or the liquid phase. But the gas over here, the oxygen, is in the vapor phase, or its gaseous form. Therefore, the major contribution of entropy should be coming from the gas, from the oxygen. Which means that when you do the calculation, if you want to calculate delta S, you only need to take care of the entropy of the oxygen. Because the entropy of gas is much greater than those for liquid and solid. So please bear in mind that this is much greater than liquid and solid. So when you look at this, delta S is mainly contributed by the entropy change of oxygen. Okay. So finally, we have the influence of pressure, but in fact, we've already mentioned this last time. If we start from DH and we're no longer dealing with constant pressure, we're dealing with constant temperature, and then we change the pressure, then we have an expression like this. And by using the relations that we use for chapter 5, it turns out that we have something like this, right? So partial H, partial P at a fixed temperature, it is in fact the volume times 1 minus alpha T. Actually, we've already derived this in chapter 5. So this is only reviewing what we've already learned. And the reason why we bring this up is because if you're dealing with a constant temperature process and when you are changing the pressure instead of changing the temperature, this is what we'll get. The delta H based on the pressure change can be calculated by that. And once you know what alpha is, then you can calculate this. If you still remember, for ideal gas, alpha is 1 over T. Therefore, for the ideal gas, this term will be 0. So there's no change in terms of enthalpy when you change the pressure. So for an ideal gas, this ratio alpha is, this is the expansion coefficient, is 1 over T. Therefore, there's no delta H. But if you're dealing with solids, you typically will have a finite value of alpha. And for instance, if you're dealing with iron, the molar volume is 7.1, and the alpha is about 3 times 10 to the minus 5 per Kelvin. If you plug that in, okay, and you try to calculate delta H, and the example in the textbook shows you that we change the pressure by 100 times. So this is a very huge pressure change from 1 atm to 100 at the constant temperature, at room temperature. We only see that the change of enthalpy is 71 joules. So this is a very small value because the same increase can be obtained by changing the temperature of iron from room temperature to 301. So there are 2 ways to change delta H, right? We can change the temperature, we can change the pressure. In the case of changing temperature, you only need to change that by 3 Kelvin in order to achieve 71 joules. But if you are dialing, when the control that you can have is pressure, you have to increase the pressure by 100 times. So it means that it's harder to control delta H by using pressure. It's much easier to do that by changing the temperature. Therefore, it is typically on this textbook or in this textbook that we're changing the temperature rather than changing the pressure. And that's the same for entropy. So if you are dealing with entropy, you start from the same equation. ds is partial S partial P at a constant temperature times dP. And you use one of the Maxwell's relations to replace that with partial V partial T with the minus sign. We've already done this before. And it turns out that delta S is only related to minus alpha V. And we integrate that over a certain range of pressure. So typically, if alpha and V are both a function of pressure, then you can calculate this. For ideal gas, of course, again, alpha is T inverse. If you put that in, this is V over T, and you integrate that, you'll retrieve the form that we've already seen. Actually, we saw this in chapter 3. We also saw this in chapter 5, and now we see this again. Okay, so we've seen this like for the third time this semester. And if you change the pressure again from 1 to 100 atm, so that's again 100 times bigger, there's only very, very small change in terms of entropy, this minus 0.002. So you can also do that by just changing 0.3 degrees of temperature. So it means that, so this is the most important remark over here. The molar enthalpy and entropy change are relatively insensitive to the changes of pressure. So if you're just changing the pressure, you typically have to change that by 100 times in order to see the same change when you change the temperature for a few degrees of Kelvin. Okay? For instance, in this case, you can change the temperature by 0.3 kelvins, but you have to change the pressure from 1 to 100 atm. So that's a huge difference. That's a huge difference. So if you want to combine these two effects, like if you want to change both the pressure and temperature, of course you can have this general formula. But typically we only look at the temperature change part. Because for most of the chemical reaction that we're going to learn in this textbook, it's going to be around 0 to 1 atm. So we're not going to enforce a lot of pressures like 100 atm onto our material systems. Therefore, typically we can ignore the last term. We only need this and this. That's the reason why last week when I said that this chapter is only about these two equations, I only write down the first term for each equation. These are not that, this term and this term are not that important. Although there might be one or two problems asking about the calculation of these two. But typically, if you are integrating over a very small range of pressure, like say just 1 to 2 atm, typically the contribution of that part is fairly, fairly small. Okay, it's very small. So typically, all those information will be given, in order for you to calculate delta H and delta S. So for condensed phase being considered over small ranges of pressure, typically volume, and this is alpha. This is not NA. This alpha can be taken as constants. Okay, so those are not the, in a small range of pressure, these are fairly constants, so you don't have to worry about that. Okay, so that's probably the end of the textbook. There are several numerical examples in the textbook. I think in this one, in the new version, if you're looking at the 6th edition, there are, I think, 4 questions or example problems. And the first qualitative problem is also very important. It's very short, but it's important. it asks you to estimate the molar heat capacity of iron silicon spinel at very high temperature. So, for instance, iron 2 silicon. This is how many? Oh, 4. So this is the first qualitative example problems. I think this is a very interesting one because typically when we talk about CP at the very beginning of this chapter, we say, okay, so CP should be close to 3R, right? And this is roughly like 24.9 joule per Kelvin mole. Should be something like this, right? But in reality, if you look closely into the textbook, this is the value for single atom material. So if you're dealing with, for instance, let us go back to this plot. You'll see that typically we look at lead, copper, silicon, diamond is purely carbon, right? If you look closely, you'll realize that for these examples, they only show you the materials with only one atom, only one species. So those are pure elements. In those cases, CP is close to 3R. But what if you're dealing with compounds or chemicals like this? Then you have to take those different contributions into account. And in this case, to make a qualitative guess, in this problem, we see that we have how many atoms? We have 2 atoms here, 4 atoms here, and 1 atom here. So in total, we have 7 atoms per mole. So it means that, in this case, we have to multiply this number by 7. So this is close to 21R. And R is around 8, right? 8 point something. So you'll end up with a number which is close to 180 or 174.6 joule per mole per Kelvin. So this is the number that you will get for this kind of chemical. Okay? So this is important information for that it's not being covered in the previous edition of the book. That if you're dealing with a material that is consisting of different kinds of atoms, you actually have to take all those atoms into account. So this is the formula unit for this kind of material, iron silicon oxide. And it has 7 atoms per mole, so therefore you have to multiply 3R by 7. So this is an example. In reality, the real value, experimental value for this one is around 200. So this is a fairly close approximation. And the second qualitative problem is similar to the derivation of partial differentiation, so I won't go through that. And I think more importantly is the quantitative example problems of this chapter. So I suggest that you go through these very carefully. For instance, the first one, The first one is about a reaction. So if you have this kind of reaction, if you have iron oxide and you put that with aluminum, then you have this reaction of becoming iron and then forming aluminum oxide. Okay? And this is allowed to proceed to completion, and which means that this is maybe a spontaneous process. And it is a exothermic, which means that it will release heat. Therefore, delta H should be negative. And this is, let's say, happening at 298 Kelvin. So if this, let's say originally this is in the solid form, right? Not sure. This is a solid form. This is in solid form. So let's say originally these are all in the solid form. And after the reaction, we know that there is a release of heat. But the releasing of the heat will further heat up the products. So the problem, the example problem here is trying to ask you that what will be the final states of these products. So through this reaction, we have a heat that is being involved, right? We will release some certain heat. And this heat can be used to melt, for instance, iron and also aluminum oxide into liquids or even vaporize them. So this is a very general example in the textbook. I think for the 6th edition, it took out, I think it takes out a very complicated one. That is originally, if you're using the last version, the example 4 is very, very complicated. But now it tries to simplify that into this simple first example. So the problem is that if you know this, then you should be able to figure out what will be the final forms of iron and aluminum oxide. So first of all, I'll go through this very quickly, that from the experiment, if you look at the appendix, you should be able to figure out how to calculate delta H. Because this is, we know that H aluminum 298 Kelvin is what? 0, right? And that's the same for here. So we don't even need to consider the enthalpy contribution from these two. So in order to figure out delta H reaction, we only need these two. So it is H aluminum oxide minus, this is 298 Kelvin, and iron oxide 298 Kelvin. And these can be found in the appendix of the textbook. At least on the textbook, it says this one is what? 700. And for iron oxide, this is 800. 400 joule per mole. Okay, so you have these two numbers. And this turns out to be minus let's say 300. So this is only the very first step, just to figure out what's the reaction heat for this process. And it turns out that this is a minus sign, which means that it's a exothermic reaction, so it is releasing heat. And we're going to see if this amount of heat is going to melt this iron and also melt this aluminum oxide. So then the textbook will give you tons of information regarding this. So basically you have to know the CP of, so now we know that we have this amount of heat. Once we know that, then we don't have to worry about the reactants. We're all looking at over here, because this heat will be used to heat up these materials, the products. So basically, the information that you need is, first of all, CP of aluminum oxide for solid. So this is already given, and the range is 298 Kelvin to the melting point, which is 2325 Kelvin. Okay, so it means that for aluminum oxide, it will be solid state or will be solid until this temperature. And for iron, it's more complicated. It has alpha, beta, and gamma. So you have three different, alpha, gamma, and delta. And then this will become liquid. So the first transformation will take place at the 1187 Kelvin. And the second one is 1664. And the melting temperature of that is 1809. Okay, so it's good that typically I want to write down all the possible values that the textbook is giving you. And then, of course, for each phase transformation, there's a delta H being involved. For instance, iron alpha to gamma phase transformation, there's a Joule 670, and we have 840 here. And for the last one, because this is a melting process, so the number should be bigger. Okay, so this is the phase transformation latent heats for each process. So basically, we want to calculate the delta H for this one and this one, and add them up to see if that is greater or less than the heat released by this reaction that we just calculate, which is, again, this minus 852,300 joule per mole. Okay, so if you go through page 188, it will ask you to calculate the change of delta H by using this formula. sorry. This is, So for each material, like for iron and aluminum oxide, you're going to go through the calculations based on this. Right? So for instance, for iron, we know that H298 should be 0 because iron at 298 should be 0. So you start from 0, and then for each phase, you have a certain CP. So for instance, this is only allowed from 298 Kelvin to 1,187 Kelvin. So if you go beyond that point, for instance, you are here, then you have to do this. You have to add this 670. And we know that this is for iron in the alpha phase, and this is iron in the gamma phase. Okay. So if you're dealing with materials at different range, please bear in mind that you have to use different CPs, and you have to use the number of the latent heat transformation. Okay, so you start from here, and you keep gradually increasing and adding up, and see if this number is still less than this one. Once the enthalpy for aluminum oxide and iron is greater than this, if the sum of enthalpy for these two are greater than this one, it means that that's the maximum point that the melting will stop. Okay, and for this one, it turns out that eventually you will have I think 0.05 moles of gas of iron, and the rest of them will be liquid, and this will also be liquid. Okay. So this is quantitative problem 1, and please bear in mind that this is probably the most important problem, and that you probably have to go through by yourself. Okay. And the problems in this textbook, I think for this chapter, it has only 10 of them, so it should be pretty straightforward. And please go through them carefully. And as you know, typically for the exam, we don't change the numbers. So they're all the same as, I mean, it's okay if you want to memorize, but it's possible that I can change the numbers. Yeah, so, but you should go through those problems carefully. 好，我们大概期中考下礼拜嘛，下礼拜我们没有课，对，所以那个到第6章，就只有第5章跟第6章而已。然后通常期中考就是第2次期中考就是很多偏微分嘛，因为你们第5章的那个作业应该就知道，就是会有很多偏微分的东西。Maxwell relations 都会给你们，所以你也不用记。就是它第5章这个什么 important formulas， 它都会考卷都会给你。对，所以我觉得最重要的是那个习题啊，就是第5章跟第6章的习题要，最好是全部都做过去，这样子考试应该就没有什么问题。然后因为我没有讲那个 Debye model 嘛，就是往年是有提一点啊，可是我想说，因为下学期就有固态物理，所以我就不讲这个 Debye model。OK。 所以这个 Debye model 的细节当然就不会考。可是那个 Einstein model 跟 Debye model 的差别，这个很重要。那每次考好像都只有一半的人答对，我也不知道为什么。这其实还蛮简单的东西。OK。
然后都考差别。
就问你 Einstein model 跟 Debye model 的差异在哪里啊？我不知道，他们可能就因为其实有些东西就是你当然计算的东西就比较不需要什么观念理解嘛，就带进去算就好了。可是不是啊，那个是结果。Einstein model 就是
从推导上的差异去讲，
它的假设就不一样啊，就是它假设到底有什么不同。对，这个是最重要的嘛。那这个是课本里面在讲 Debye model 的时候一开始就提到的。对，所以5、6章哦，大概是就是反正我们只考5、6章的内容。那个因为我下礼拜不在，所以你们如果有人有想要停休，或者说要有疑问，就是说会不会不过的，可以再找时间来跟我谈一下。你们停休是到什么时候啊？已经结束了是不是？12月7号，所以还有一段时间。对，你们可以再想看看，对，再想看看。那个考卷记得交给那个助教，因为还要回去登记分数，你不交给他就没分数。